Hi, I'm Sid,
Hi, I'm Rong.
and today we are going to talk about full SQL semantics in Pinot and introduce Pinot's V2 query engine to everyone. I'm going to start off by talking about the workings of the existing engine, and then Rong is going to come back up to talk about the details of the V2 query engine. All right, see you in a few, Rong.
Hi, see you.
All right, so let's get started with Pinot's existing query engine. So Pinot is like a distributed OLAP engine for low latency analytics using SQL. Each table stored in Pinot is sharded or distributed into segments and replicated onto multiple servers. Each segment stores the data in columnar format on disk and in memory. Now, a little bit about why columnar format. So OLAP engines are typically focused on high-speed analytics. Query processes fewer columns across a large number of rows, and the workload is generally focused on aggregating, analyzing, or number crunching a large number of rows at a column level. And columnar format actually helps with better utilization of the I/O bandwidth as well as the CPU memory bandwidth. And the format is very much amenable to vectorization, so it can help with efficiency for analytical workloads. So consider Pinot segment as like a persistent data structure that's storing your data in columnar format, and it comprises of multiple substructures that I'm going to talk about in the next slide. Yeah, so here, as you can see, a single Pinot segment has multiple data structures, starting off with forward index, which is basically stores the raw data of the column, which can be dictionary encoded or raw. Then you also have a dictionary for the column. Then depending upon the requirements for the query workload, we may have a couple of indexes. In this example, as you can see, we have an inverted index. And for another column, we again have a forward index, which in this case is compressed using ZSTD, and we also have a text index on that column. So this is an example of how a segment is arranged on disk as comprising of multiple buffers, which are columnar in nature. And each structure is basically a buffer. You can call it as like an off-heap buffer, which is either memory mapped or direct, with the exception being of inverted index for the consuming real-time segment, which is on heap. And data source is like an abstraction that we use in the code to access all these buffers during query execution. And all of the transient memory that we allocate during the life of a query during execution is allocated on JVM heap. So moving on, as you can see here, we have input data, which is like your first name on the left-hand side, like Adam, John, Jane. And then you can see how that is materialized into a segment format. You can see starting off with the forward index. The forward index stores the dictionary IDs for the column data. The dictionary basically stores each of the unique values. So the length of the dictionary is equal to the length of the cardinality or the number of unique values in the column. And each row in the forward index basically has the dictionary ID. So taking an example of Jane, right? So Jane's dictionary ID is 1, and then that is stored at the corresponding place in the forward index. Now, on the other hand, we have inverted index, which is essentially a mapping from your dictionary ID, the corresponding bitmap of doc IDs. So basically, if I want to find out or look up where Adam is occurring in my segment, I'll first look up the dictionary to find out the dictionary ID, and then I'm going to look up the inverted index with the dictionary ID to find the set of doc IDs. Now, let's talk a little bit about how the query compilation works in Pinot's existing engine. So this happens on Broker. We get a SQL query string, which is then fed into Calcite SQL parser, which is our parser written on top of Apache Calcite. It basically generates an abstract syntax tree, and we get a root node of that AST, which is the SQL node. And then we walk down that SQL node and generate our internal representation of the compiled query, which we called as Pinot query. So Calcite, basically a little bit about Calcite, it has SQL grammar defined as LL grammar, which is basically a free marker template-based file, and it is very much extendable. And Java CC, which is another tool, it compiles the parser.jj file into basically a runtime generated Java code. And parser is basically used to accept, reject the SQL based on dialect, compliance, and whatever conformance we want our parser to accept. Now, from compilation, let's move on to execution planning. So the compiled query that is generated by Broker, it is basically created as a thrift object. So it is serialized using thrift, and then this request is sent to each server by the Broker along with a list of segments that the server is supposed to execute the query on. The first thing the server does is that it invokes the pruning phase. So pruning is basically used as an optimization to eliminate unnecessary segments to improve performance. The couple of things that we use for segment pruning are like column level statistics that are maintained in the on-disk metadata as part of each segment. So for example, we can use the columns min-max value metadata and corresponding with the filters used in the query, for example, equals in, we can decide whether this segment should be considered for the query or it can be ignored or pruned. Another strategy that we use is that on a column, if we have a Bloom filter stored in the segment, then again, for equals or in filter operators, we can decide whether the value that we are looking for in the query predicate has a probability of occurring in the column at all, in the segment, or not at all. So after the pruning phase is over, the server basically generates per segment optimized physical execution plan. So this is basically very important and one of the key aspects of our execution engine. So for each candidate segment that the server is supposed to execute the query on, right, it builds an execution plan, or we call it as an operator tree or operator chain, which is optimized to execute the query on a given segment. And the server basically considers different kinds of information about each segment to generate an optimized physical execution plan. Some of the information that we consider is basically column cardinality, the kind of indexes that column has in the segment, and other metadata. Once the physical execution plan is generated, how does the server basically execute the operator tree? Consider it as like a block-based pipeline processing. So each child operator basically returns a block, which is an abstraction. It contains some processed data, and that is pipelined into the parent operator. And then all relational operators basically implement this get next block interface, which is basically invoked in the pipelined execution. Consider block is like in a collection of column vectors, and it could be like a raw scan data, or it could be filtered data coming out of the filter operator. It could be transformed. So for example, if you want to transform the source data using some custom function, then we have transform operator for that. Or it could be just like as is simple projected data. And each block basically considers 10,000 records at a time, and that is pipelined into the parent operator during the life of the query. So here you can see a simple example of how the operator chain may look like. So here the example is given for a simple aggregate query, which uses filters as well, and we are doing an explain plan for that query. As you can see, the filter tree is basically comprising of the AND operator, which is the root, and it has two leaf operators. One is basically using an index-based filtering on one of the columns, and the another one is basically using scan-based for the range predicate because we don't have an index for that. And then the output of the filter operator is fed into the project, and then transform because we also have an addition transform inside the sum aggregate. And then the transformed output is fed into the aggregate operator, which is then combined by the server. And finally, all of this result is sent back to the broker, which finally reduces the output across servers and returns the query result. So now a little bit about how the parallel query execution happens on the server. So on the thread pool side, each query basically gets a single main thread, you can call it a runner thread, and multiple worker threads. And the thread pool is created during server start. And so until a runner thread basically picks up the query, when the query lands on the server, it basically sits in some form of a queue. And each server executes the operator trees across segments using multiple threads. So as you can see in the diagram below, we have a root operator called as combine operator, which is basically controlled by the single runner thread. And under that, we have, in this example, 3 worker threads. And each of the worker threads are basically executing the operator chain across multiple segments. So each thread basically executes the operator chain across segments sequentially, and then the output of these threads is then combined by the combine operator, and that becomes the server response for that particular query from a given server. Each server basically returns this response back to the broker, and broker has the job for reducing or merging the response from different servers and returns the final query response to the user. Now let's talk a little bit about the current state of join support in our engine. We have this inbuilt function called as lookup, and it does not support full ANSI SQL join. The main usage of this function is basically for result decoration or enrichment. So essentially, let's say you have a fact table and quite a few smaller dimension tables. So lookup UDF function basically allows you to perform join on the primary key. So as you can see, the syntax is something like you provide the dimension table name and the column to lookup. The column to lookup is essentially the column that you're going to be outputting as part of the lookup function. And then you provide a pairs of basically the join key column name from your dimension table and the join key column value from the fact table. So the advantages of the current approach is basically the join query does not require any data movement or exchange between servers. On the other hand, the disadvantages are that it offers limited flexibility. So as a user, you need to know the join keys upfront because they must be identified in the table config of the dimension table when you set up the table. Then the dimension tables should ideally be in the order of few hundreds of megabytes because the constraint is that the dimension table must be fully co-located on all replicas of fact table and loaded in memory on the JVM heap. So because it's on heap, so ideally this approach will work only for smaller dimension tables. So let's walk through an example in the next slide. So here, like you can see, right, as I explained in the previous slide, we have a fact table, the orders table, and like typical table, it is distributed across the segments of that table are distributed and replicated on 4 servers. Then we have a dimension table, a smaller table called customers. And as I mentioned, all the 3 segments of the customers table are sitting on all of the hosts of the fact table. So basically, it is fully replicated on each of the hosts. And here's a simple query. So basically, we want to find the total amount of order value for each customer tier. So what we want to do is that we want to perform a lookup join on the dimension table called as customers. The second, we want to project out the tier column from the customer table, which is why that's your second argument. And the join is going to be performed on the customer ID because that's the column that is present in both your fact table as well as the dimension table. And we're basically doing some sort of equality join that wherever the customer ID is matching between the fact table and the dimension table, give me the value of the tier column. Right, and that basically is the output of your lookup function, and then that is basically combined with the sum aggregate function on the orders table, and finally the regular query processing regarding group by and order by. So as you can see in the 4th server, I have explained that the lookup join execution is basically like a local in-memory hash join. So the hash table is preloaded at server start for the dimension table, and it basically goes over that and tries to perform equality join using the corresponding set of segments from the fact table that are there on that server. Now, let's talk about a few challenges with this current approach. So one of the things is that we are not really leveraging the compute intelligently here to execute a join query. All of the heavy lifting is essentially being done by the servers, and then we are sending back the results, just like any other Pinot query, back to the broker for it to do final reduce. So first is that the broker can actually become a bottleneck depending upon the amount of data that each server is kind of feeding into the broker. Secondly, the servers a query may not itself scale because we are only leveraging a few set of servers and we are not actually distributing the workload across different servers. So that's basically the challenge with this approach. And for that, we came up with this new query engine, the V2, where, as you can see, apart from the leaf layer of the servers, we also have an intermediary layer of servers, which gives us more compute. And then we have data exchange and shuffle. And now Rong is going to come up and talk about the internals of this engine, the design and implementation details.
Thank you, Sid. Hi, I'm Rong again. So here is my presentation to talk a little bit more into the details on the Query Engine V2's implementations. So let's look at the components that the V2 engine consists of. So the V2 engine is actually built on top of the existing Pinot Query V1 engine. A lot of the components are actually being reused. But in order to satisfy the requirements for us to create an intermediate results or intermediate stage executional servers set, we are actually going to leverage a little bit more than just the Kelsa SQL parser. In this specific example, we are actually using not just the parser, but also the logical planners, optimizers, and also we customize our own specific logical planner stage, which is called the stage planner. So as you can see in this diagrams, the SQL string comes in, it goes through the exact same SQL parser that Sid just presented in the V1 engine. But after that, we are actually utilizing the calc-size logical plan to create an actual logical planner, which consists of all the information about the tables, about the operators. After that, we apply a bunch of optimizer rules, and then we feed it into our customizable stage planner. The stage planner basically breaks the logical plan into multiple different parts and then determine whether each one of these parts should be executed in a leaf node or it should be executed in a kind of like intermediate role. After that, we will have a query dispatcher, which acts kind of like a centralized brain for this query engine execution that dispatch out the distributable plans to each one of the servers, which they will execute each one of these plans individually. So let's look at the query planning phase. As I can just explain, the logical plan basically executes the Apache calc-size logical planner and construct a relational plan. After that, the stage planner splits this into multiple different stages based on whether we need actually a data shuffling across different type of servers. And then afterwards, the dispatcher basically attach the information regarding which stage should be executed on what set of servers, and then send it out as a distributable plan. Here, let's go back to the examples that Sid just explained. Let's say we have an order status table which trying to join an inner join with a customer table, which is kind of like a dimension table. A dimension table is relatively smaller, but in the same time, if we have both of these tables scale up 10x, 100x, we won't be able to use the lookup join algorithm. So in this case, we're actually writing a very standardized SQL join algorithm or join syntax, where you wanted to join the order status table with the customer tables based on a user ID key, but we also have some kind of predicates we wanted to ensure. Now, a typical logical plan is being generated on the right-hand side. As you can see, is a projection, a future is being executed. Then a logical join is actually being fed in by a logical table scan on both of the table sides, on the order status side or on the customer side. Now, next is actually the query optimization plan that comes in. So this is actually largely based on the fact that Pinot has such a great and indexing mechanisms, filter mechanisms, etc., that makes its leaf stage extremely fast. So built on top of that, we can actually build a relatively simple rule-based optimizer, which actually is extension of the standardized core plan optimizer provided by calc-size, such as predicated pushdowns, join aggregate swapping, transformations, etc., So all of these algorithms are actually basically being applied given the fact that a lot of our executions are better executed on more performance in the leaf node rather than in the intermediate node. So on top of that, we also apply a bunch of Pinot-specific rules so that we can actually create our distributed plan in a more efficient fashion. So going back to the example that I just presented, in this case, a lot of these features are actually better prepared by push them down across the join stage into the table scan stage. So in this case, you're sending less data over the wire to the join node, but also at the same time, you can leverage the inverted index or the other types of index mechanisms on the server side so that you can actually done processing much faster. Now let's talk about the distributed runtime. So we are actually reusing a very similar executional runtimes as Sid just mentions on the V1 engines. So the servers are actually kind of being wrapped around with a thin layer of query runners. So this query runners actually is executing either a leaf stage or intermediate stage executional plans. The leaf stage was actually being executed in the current Pinot stage V1 engine, but the intermediate stage was actually being executed in kind of like a separate thread pools, so that it actually is being executed in a much isolated fashion. So with this setup, the executors are actually homogeneous. All of the executors on all of the servers are exactly the same, but they are operating on heterogeneous data, which means that each one of these operators will have the information regarding what type of data they are actually operating on. With this, we also need to have a way to exchange the data in between servers, and that's where the data exchange manager comes in. So we are actually trying to unify this information transportation in between servers by utilizing the data exchange managers. So regardless whether you are executing in leaf stage or intermediate stage, they will all consider as kind of like a data blocks being coming in, just like the block concept that Sid just mentioned in the V1 engine. So what happens afterwards is the stage planner kicks in, and then looking at this optimize the logical plan and then break it down into 3 different stages. As you can see in the top is the join and projectional stage, and on the bottom left is the first leaf stage of the server groups. And on the bottom right is the leaf stage of the server group 2. Next, we will actually dispatch these informations into some kind of query dispatchers. So what happens here is that query dispatchers takes each one of these executional plans and then send them to the corresponding servers, which actually has data on it, or at any of the intermediate servers that actually can be executed via data exchanges. So in this case, the bottom left is again the server group 1, bottom right is again the server group 2, and then the intermediate layer is actually executing the server group 3. So what happened here is we're going to walk through with some of the examples regarding how exactly these data are actually being transferred. So the first stage, we're actually evaluating the leaf stages. So both the order status table scan and the customer table scan will be executed first. First of all, we are actually applying the where clause, so to filter out all of the IC count that is less than 10. In this case, 3 of the rows, 1 on the server 1 and 2 on server 2 are actually being crossed out. And then at the same time, the customer table, we are actually filter out using the LTO value larger than 5, which also cross out 3 of the rows. Next, we are actually sending all of these data through the intermediate data exchanges to the intermediary servers. What we are actually doing here is hashing the result exactly by the join keys on both of the tables. So in this case, for example, value 1 on the join key will go to intermediate server 1, value 2 will actually go to the server 2, and value 3 will actually go to intermediate server 3. Afterwards, the join can actually perform locally, just as the local join execution, as Sid mentioned on executor V1, but instead of actually needs to distribute the dimension table in advance with the primary key and also need to be loaded in memory. Now all of these intermediary servers can load dynamically depending on what exactly the query plan is. In this case, we're actually joining nothing on server 1 because there's nothing on the right-hand side. We are joining everything on the server 2, so we produce 4 rows, and then we are actually joining just 1 rows on server 3. Next stage is sending everything back to the broker, assemble the final result, and this result is sending back to the user. Here is a summary of the V2 engines and our next steps. The V2 engine is enabling users to perform analytics in Pinot that is previously not possible. It includes joins, join after group buys after joins, running subqueries, etc., etc. We're transferring the bottleneck from the broker reduce stage into an intermediary computational stage, which we can add arbitrary number of executional servers onto it. We also maintains the end-to-end low latency query executions by running a relatively efficient rule-based optimizer so that we don't have to run complex executions before the query actually gets executed. Towards full SQL semantics is actually what the V2 engine is planning to go with. Because with the intermediary computational stages, they can even be cascaded into multiple different layers, 3 stages, 4 stages, etc., etc. This opens up with a lot of mix and match of complex operations such as subqueries, cross joins, lateral expansions, table functions, or window aggregate, or even metric recognize, or even other complex event analysis. So here is our roadmaps. We are actually here on Q2 2022. Our beta test has finally been stabilized, and then we have released our build on Docker images. It's now available for everyone to try it out at home. By end of the year, we will actually reach feature compatibilities with the current Pinot executional semantics. We will add a lot more SQL features like order bys, having limits, etc., etc. By early 2023, we are actually aiming at V2 as our default engine so that the performance and stability compatible is with the current Pinot engines. And by late 2023, we are expecting to reach full SQL semantics with all of the complex event and semantics analysis. We are also adding a pipeline executional engines afterwards. So thank you everyone for listening, and thank you Sid for the presentation.
Thank you, Rong, and thanks everyone. Hope you have a great rest of your summit.